All right, welcome to The Explainer. Today we're going to talk about something that's quietly running in the background of your life, powering everything from movie recommendations to, believe it or not, medical diagnoses. We are breaking down decision trees.
So let's just dive right in with a huge question. How do machines actually make these smart decisions? You know, the ones that decide who gets into a university or whether you get approved for a loan. How do we teach a computer to make those kinds of complex choices that really truly impact our lives?
Okay, so the whole journey really starts with this core idea in AI called supervised learning. And honestly, the best way to think about it is like you're teaching a computer, but you're giving it a study guide that already has all the answers filled in. It's basically learning by example.
So here's the secret sauce. We feed the algorithm a whole bunch of data where we already know the correct outcomes. The machine just chews on all this labeled data, starts to see the hidden patterns, and then it gets ready to make its own predictions on brand new data it's never seen before.
And that brings us right to the star of our show today, something called a decision tree. It's this super intuitive model, really powerful, that basically works the same way our own brains make decisions. It's all laid out just like a flowchart. You know what? The best way to really understand this is to just build one together.
All right, let's do it. We're going to build a decision tree right here, from scratch. And our goal? To figure out which student should get admitted to a university.
First things first, we need our training data. So what you're looking at here is just a sample of past applicants. We've got their GPA, their test scores, and, most importantly, the final decision that was made for each of them. This is that labeled data we were talking about. This is what our model is going to learn from.
Okay, so to actually build our tree, we're going to follow a process that's based on something called Hunt's algorithm. Don't worry about the name, it's actually super straightforward. It's just a few logical steps. You pick a place to start, you split the data with a simple yes or no question, you check if the new groups are all sorted out, and if they're not, you just do it again.
All right, step one. We start at the very top of our tree, which is called the root node, and we're going to start with GPA. Now you might be wondering, how in the world did the computer pick the rule, is the GPA greater than 3.55? Well, it's not random. The algorithm actually tests a whole bunch of different split points and picks the one that does the best job of sorting the data, the one that creates the most order. In our case, 3.55 was the magic number.
And just look at what that one simple question did. It instantly split our applicants into two groups. And check this out. The group on the right, every single person in that group has the exact same outcome. Weight. We call that a pure node. It's perfectly sorted. So that branch of the tree, it's done. Mission accomplished.
Okay, but what about the left branch? That one's still a mix, right? It's impure. We've got some admit and some decline decisions all jumbled together. So what do? We just repeat the process. The algorithm looks only at that messy group and finds the next best question to ask. And this time, it's about the test score. Is it over 900?
And boom, just like that, we're finished. That second question perfectly sorted everybody that was left. All the final groups at the bottom of the tree, and we call those leaf nodes, are now totally pure. We've actually built a complete, working model right from our data. How cool is that?
So, okay, we've got this nice little tree. But so what? What's the point? Well, this is where the magic happens. The real power comes from using this tree to make predictions on new people, on data the model has never, ever seen before.
Let's put it to the test right now. Imagine a new applicant comes along. They've got a GPA of 3.6 and a test score of 91. What's our prediction going to be?
It's super simple. We just follow the branches. First question, is their 3.6 GPA greater than 3.55? Yep, so we go left. Next question, is their 901 test score greater than 900? Yes, it is, so we go left again. And where do we end up? On a leaf node that says admit, and that's it. That's our prediction. Now, this brings up a really important point, a key trade-off. The best thing about decision trees is how clear they are. You can literally see the logic. But there's a catch. They can sometimes get too good at understanding the training data, almost like they've memorized it. This is a classic problem called overfitting, and it can make the model less accurate on new real-world data. Now, data scientists have clever ways to deal with this, like pruning the tree to keep it simple, or even combining hundreds of trees into what's called a random forest for a much stronger prediction. So, building one by hand, like we just did, it's awesome for really understanding how it works. But let's be real. In the real world, you're dealing with huge amounts of data. So, of course, we let the computers do all the heavy lifting.
And this is where having a standardized workflow is absolutely critical.
And luckily, with powerful tools like Python's scikit-learn library, that process is pretty much set in stone. First, you get your data ready, you split it into a set for training the model and another for testing it. Then you build the model, or what we call fitting it to the training data. And the final step, you see how well it does on that test data it was never shown.
But that brings up a really important question, right? After the computer builds this whole tree, how do we actually know if it's any good? I mean, how can we measure its performance and actually trust the predictions it's making?
Well, the answer is a tool with, honestly, one of the best names in data science, the confusion matrix. Seriously, the best way to think of it is just as a report card for your model. It's a simple table that shows you exactly where the model nailed it and, this is the important part, exactly where it got confused.
Okay, let's take a look at one. See that diagonal line of numbers going from the top left to the bottom right? Those are all the times the model was correct. That's where its prediction matched the real outcome. Everything else, all the numbers off that diagonal, those are mistakes. And this is so powerful because it doesn't just give you a simple accuracy score. It shows you the exact type of mistakes the model is making. And knowing that is absolutely crucial for making it better.
So let's step back for a second and look at the big picture. We've gone from asking a simple question to building a model and even testing it. Why does a concept that seems so straightforward matter so much in the grand scheme of things?
It's because decision trees really are a foundational building block of machine learning. They're like this transparent, easy-to-understand bridge that takes a huge, messy pile of data and turns it into clear, actionable insights, the kind of insights that drive actual, real-world decisions.
And that right there is their superpower. You know, unlike a lot of those complex black box AI models where the internal logic is a total mystery, decision trees are transparent. You can follow the logic from top to bottom. And it's that accessibility, that clarity, that makes them such a popular tool for everyone from hardcore data scientists to business analysts. And that leaves us with one last, and maybe most important thing to think about. As we let these automated systems make more and more decisions about our lives, about our loans, our jobs, even our healthcare, we're facing a huge new challenge. When an algorithm makes a choice based on the rules it's learned, who's responsible for making sure those rules are fair? And ultimately, who is accountable for the outcome?